The F-22 Raptor is the most advanced of its breed, built around the first look, first shot, first kill ethos. The Raptor is a killing machine, just like the name implies. It's even more deadly when it gets out there and does the job. Deadly and undetectable at long range, this breathtaking fifth-generation fighter blends unmatched dogfighting with precision strike ground attack capabilities. Confidence lies in the fact these goals are achievable as a result of synergistic combination of characteristics and capabilities, including low observables, also known as stealth, the ability to cruise at supersonic speeds, or Supercruise, over long range and without the use of afterburners, and an integrated and highly sophisticated avionics unit. Additionally, the F-22A has been designed to be more maneuverable, better armed, more reliable, more easily maintained, more readily supportable, and more capable in the air-to-ground mission than any other comparable aircraft in history. Throughout the 1960s and 70s, the Soviets developed different missiles to attack in different altitude bands. You couldn't fly under the missile threat, you couldn't fly over the missile threat, you had to deal with the missile threat. One way to do that is to make suppression of enemy air defense, that is, destroying the missile sites in the radars, the most important mission for the Air Force. By the 1970s, air superiority had re-emerged as a top priority, and the U.S. Air Force committed to building its first pure air superiority fighter, an aircraft that would eventually become the F-15 Eagle. But just as the F-15s became operational in 1978, alarming new evidence suggested that the new fighter's superiority might only be temporary. Reconnaissance satellites had photographed several new fighter prototypes, the Mikoyan MiG-29 and Sukhoi T-10, at the Ramenskoye Flight Test Center outside of a small city of Zhukovsky, about 40 miles southeast of Moscow. This new generation of Russian fighters represented a significant improvement in capability over anything previously observed by U.S. intelligence services. It was obvious to all concerned that a new air-to-air combat platform would be required to counter the new threat these new Russian aircrafts represented. The Sukhoi T-10 came as a huge shock to Western analysts. It was bigger than the F-15 and far bigger than any previous Soviet-built fighter. If the MiG-29 had concerned the American military establishment, the existence of the Sukhoi T-10 set alarm bells ringing. These are very good aircraft. Just weeks into his first term, America's 40th president increased U.S. defense spending by $32.5 billion and began the rearmament of the United States on a colossal scale.
The goal is world peace. It is absolutely essential that we increase our spending for national defense if we're to preserve the peace.
As Reagan and Brezhnev squared up, the U.S. Air Force concluded that it would urgently need a new replacement for its F-15, an advanced tactical fighter, or ATF, that would have no equal. As American planners start to develop the concept of air-land battle to fight World War III, the U.S. Air Force starts to think about the kind of equipment it wants to have when it comes to fighting the war. Two sub-projects were established under this banner: the Advanced Tactical Fighter, which included concept and technology development, 7 airframe companies, being Boeing, General Dynamics, Grumman, Lockheed, McDonnell Douglas, Northrop, and Rockwell. Each received concept development investigation contracts for $1 million. And the Joint Fighter Engine, which was an engine technology demonstration program to be managed jointly with the U.S. Navy, Pratt & Whitney, and General Electric, each received contracts valued at $202 million during September of 1983. The 7 competing companies submitted some 19 conceptual designs. From these, it was concluded that the ideal air-to-air platform would offer low observables in combination with Supercruise and superior maneuverability. Analysis of air-to-air combat in Vietnam, called the Red Baron Study, had kickstarted a race for stealth. The principle of stealth technology is to literally make an aeroplane invisible to the enemy. An aircraft's shape must reflect incoming radio waves away from the enemy radar, rather than towards it. To further increase low observable characteristics, An airplane is then covered in materials that absorb radar signals, further reducing its visibility on radar screens. Leading the way in stealth technology was Lockheed's Skunk Works division. In 1977, amid unprecedented security, Lockheed had flown a prototype of the world's first stealth fighter. The U.S. Air Force decided that any new fighter must incorporate stealth technology, and identified two other areas in which a future air superiority fighter should excel. The challenge had been issued. Now, it was up to the finest aviation manufacturers in the world to respond. The Advanced Tactical Fighter program was about to begin, and the Raptor, America's fifth-generation fighter, was about to be hatched. By 1983, U.S.-Soviet relations had reached a new low. Following Leonid Brezhnev's death, the Politburo, now controlled by ex-KGB boss Yuri Andropov, had been labeled by Reagan as the focus of evil in the modern world. That August, when Korean airline Flight 007 on its way to Seoul from New York strayed several hundred miles off course into Soviet airspace, Russia acted. A fighter was sent up, and the civilian airliner with 269 people on board was shot down. A shooting down of KAL-007 sent shockwaves around the world, straining international relations almost at a breaking point. Reagan's reaction to the crisis strengthened U.S. conviction that stealth would now be the prime requirement for America's new fighter. Following some four initial drafts, the basic framework for the ATF requirement, calling for a radius of action of approximately 800 miles, supersonic cruise capability of 1.4 to 1.5 Mach, a 2,000 feet runway requirement, a gross takeoff weight of 50,000 pounds, and a unit cost of no more than $40 million in 1985 dollars was released to industry. Importantly, implied in the proposal was a requirement that the ATF life cycle cost be at least as good as, if not better than, the McDonnell Douglas F-15. It was concluded that Lockheed and Northrop's submissions were superior to those of Boeing, General Dynamics, and McDonnell Douglas. Lockheed had conducted consortium discussions with Boeing and General Dynamics as early as June of 1986, but did not formalize an agreement with its partners until the following October 13th. Consequently, Lockheed assigned Sherman Mullen as general manager for the ATF Team Program Office. Mullen would direct Lockheed in the prime contractor role and consequently take advantage of the unique technical strengths represented by Boeing and General Dynamics. Northrop, some 2 weeks later, followed suit by serving as lead on team with McDonnell Douglas. Thus, by default, the two consortia were selected on October 31, 1986, to build two prototypes, each to complete in revised demonstration and validation phase. Lockheed, under a $691 million contract, would build two of what later would become its Model 1132 aircraft under the official Air Force designation YF-22. Northrop, under a similar $691 million contract, would build two of its N-14 prototypes under the official Air Force designation YF-23. And in 1990, just months after the disintegration of the Soviet Union, the shapes of the two rival designs were finally unveiled. Northrop's version, called the YF-23, closely resembled its original design. In contrast, Lockheed's design, called the YF-22, seemed surprisingly conventional, with four-tail surfaces, vectored thrust, a broad solid body, and a conventional wing. But unlike Lockheed's other stealth aircraft, the F-117 radar-absorbent materials were not applied over the whole of the F-A-22, but used selectively on its edges, cavities, and crucial surface areas. The F-22 carries its weapons internally. 4 weapon bays are hidden in the central mid-body section. 6 missiles can be carried in the ventral bays, which are covered by bifold doors. The side bays will each hold 1 Sidewinder missile, carried on a trapeze launcher. The mid-body section also houses the fighter's landing gear and complex inlet ducts. Attached to the mid-body is the forebody, which accommodates the cockpit and advanced avionics. Both the YF-23 and the YF-22 are impressive-looking machines. but their performance still needs to be tested. The most crucial stage of the competition is still to come, the flight testing. Northrop was first in the air. In August 1990, flown by Paul Metz, the YF-23 got airborne. The test was a huge success. But Lockheed was quick to respond, and on September the 29th, at Edwards Air Force Base in California, Lockheed's chief test pilot Dave Ferguson prepared the Raptor for its maiden flight. Over the next 3 months, the Raptor underwent a whole series of tests. The Air Force required both teams to give them performance projections, and they were actually going to compare that with what the planes actually did in flight subsonic and supersonic at different altitudes and so forth. The winner of this stage would earn a contract for 650 aircraft. The decision would hinge not just on what the contractors promised, but on the Air Force's confidence in their ability to deliver. During flight testing, the Raptor had beaten Northrop's YF-23 in a number of crucial performance areas. The YF-22 had clearly shown that in every category it was far superior to any existing fighter. The Air Force was very impressed by what Lockheed had done, but their flight test program was very aggressive. They flew hard and fast. They flew many more hours and sorties than Northrop did, and all of that gave the Air Force confidence that they knew what they were doing, and they could build a superior plane. But it would be events in 1991 that would carve out the Raptor's future. 22 minutes after midnight on January the 17th, 1991, Lockheed's stealth F-117 spearheaded U.S. strikes against Saddam Hussein's regime. The performance of Lockheed's stealth bombers during Operation Desert Storm would give the company and its aircraft some priceless publicity. The F-15, the aircraft destined to be replaced by the ATF, had emphatically confirmed its status as the foremost air superiority fighter in the world. Now, it appeared that the need for an advanced stealth fighter, the F-22, might be totally unfounded. But not everyone agrees. By April 1991, bogged down by the F-15 debate, the U.S. Air Force prepares to announce the winner of the Advanced Tactical Fighter contract. But would the Raptor be able to emerge from the controversy unscathed? After the Dem-Val flight test of the prototypes, Secretary of the USAF Donald Rice announced the Lockheed team and Pratt & Whitney as the winners of the ATF and engine competitions. The YF-23 design was considered stealthier and faster, while the YF-22, with its thrust-vectoring nozzles, was more maneuverable as well as less expensive and risky. Having won the contract, Lockheed announced that it intended to locate the F-22's headquarters in Georgia, where the Raptor's forward fuselage would be built. General Dynamics were to build the F-22's mid-body section in Fort Worth, Texas, and Boeing would manufacture the wings and tail in Seattle, Washington. Follow-on work using this aircraft took place at the Edwards Air Force Base. It was to consist of an additional 100 hours of flying time, or approximately 25 flights to expand the YF-22A's flight envelope and explore select envelope segments in greater detail. But on April 25, 1992, the program hit its first major snag. During preliminary testing, the unthinkable happened. A YF-22 flown by Tom Morganfield crashed just after takeoff. The aircraft hit the runway with the landing gear up and slid approximately 8,000 feet and caught fire. Despite the loss of the stealth aircraft, the program had achieved its major goals. 10 million man-hours of analysis, 4,000 hours of radar testing, and hundreds of hours of flight testing had gone into the development of the aircraft, even before construction was given the go. In fact, the F-22 has accomplished more flight testing than any other fighter prior to full-scale production. On April 9th, the first F-22A, officially named Raptor, an earlier attempt to make the name of the aircraft superstar failed in 1991, was rolled out in a public ceremony at Lockheed Martin's Marietta, Georgia facility for the first time. Now, Air Force pilots would get the opportunity to check up on the new aircraft for themselves. First flown by the Air Force in 1997, pilots at Edwards Air Force Base have surpassed 2,000 flight test hours in more than 900 missions. One of the key advances in the Raptor's design is its advanced cockpit and integrated avionics system. Key mission systems include Sanders/General Electric Electronic Warfare System, Martin Marietta Infrared and Ultraviolet Missile Launch Detector, Westinghouse/Texas Instruments Active Electronically Scanned Array Radar, TRW Communication/Navigation/Identification Suite, and Long Range Advanced IRST. The radio frequency receivers of the Electronic Support Measures System give the aircraft the ability to perform intelligence, surveillance, and reconnaissance tasks. The F-22 has a glass cockpit with all digital flight instruments. The monochrome head-up display offers a wide field of view and serves as a primary flight instrument. Information is also displayed upon 6-color liquid crystal display, or LCD panels. This airplane displays information to you. It gives you knowledge of the battle space. It's all about seeing what's out there in front of you and being able to make the right decisions about what to engage and when to engage it. The ejection seat is a version of the ACES-2, commonly used in USAF aircraft, with a center-mounted ejection control. The Raptor carries a formidable array of ordnance. The F-22 has 3 internal weapon bays, a large main bay on the bottom of the fuselage, and 2 smaller bays on the sides of the fuselage aft of the engine inlets. The main bay is split along the center line and can accommodate 6 launchers for beyond visual range missiles, and each side bay has a launcher for short-range missiles. The primary air-to-air missiles are the AIM-120 AMRAAM and the AIM-9 Sidewinder, with planned integration of the AIM-260 JATM. Missile launches require the bay doors to be open for less than a second, during which pneumatic or hydraulic arms push missiles clear of the aircraft. This is to reduce vulnerability to detection and to deploy missiles during high-speed flight. While the F-22 typically carries weapons internally, the wings include 4 hardpoints, each rated to handle 5,000 pounds or 2,300 kilos. Each hardpoint can accommodate a pylon that can carry a detachable 600-gallon or 2,270-liter external fuel tank for a launcher holding 2 air-to-air missiles. And to complement the Raptor's armament of 8 missiles, the fighter also has a gun. An internally mounted M61A2 Vulcan 20mm rotary cannon is embedded in the airplane's right wing root, with the muzzle covered by a retractable door. The radar projection of the cannon's fire path is displayed on the pilot's head-up display. But since Desert Storm, critics of the F-22 program claim that the F-15 Eagle, destined to be replaced by the Raptor, already had the attributes necessary to remain the world's preeminent air superiority fighter. In March 2003, supporters of the F-15 got the opportunity to see whether or not the Eagle was still the best fighter in the sky. 5 F-15s would go head-to-head with a single Raptor. Although no missiles would be used during the exercise, the sorties would closely resemble actual combat. No quarter would be given by either side. This was a kill or be killed exercise. All 5 F-15s are flown by experienced F-22 pilots. One by one, the Raptor brings them down. In combat testing with F-15s, the F-22 Raptor has emphatically proven its doubters wrong. In December 2005, the U.S. Air Force announced that the F-22 had achieved initial operational capability. During exercise Northern Edge in Alaska in June 2006, in simulated combat exercises, 12 F-22s downed 108 adversaries with no losses. In the exercises, the F-22 amassed 241 kills against 2 losses in air-to-air combat, with neither loss being an F-22. The F-22 cannot be exported under U.S. federal law to protect its stealth technology and classified features. Customers for U.S. fighters are acquiring earlier designs such as the F-15 Eagle and F-16 Fighting Falcon, or the newer F-35 Lightning II, which contains technology from the F-22, but was designed to be cheaper, more flexible, and available for export. The USAF had originally planned to buy a total of 750 ATFs. In 2009, the program was cut to 187 operational aircraft due to high costs, a lack of air-to-air missions due to the focus on counterinsurgency operations at the time of production, a ban on exports, and development of the more affordable and versatile F-35, with the last F-22 delivered in 2012. America's F-22 Raptor was created out of the Cold War fear that the Russian-made fighters would sweep aside the F-15s. The United States Air Force is the only operator of the F-22. As of August 2022, it has 183 aircraft in its inventory. In today's changing world, there are few certainties, but the rule of the Raptor, America's air dominance fighter of the skies, is one of them.
Development of an airplane is really a packaging problem. It's the same problem that the supermarket has and how many pork chops can you put in a package. But in packaging an airplane, particularly a supersonic airplane, they have to be packaged and arranged in such a way that you don't compromise the supersonic drag. And in that, the components have to be arranged so that the volume buildup of the airplane is smooth. And that's why the lines have to be smooth. RCS design is the same way. Radar loves a flat plate or a sharp edge because it bounces off that flat plate, just like the glint on a windshield, right back in your eyes, and the radar instantly sees that return, or a sharp edge. So we want to avoid or at least minimize the number of sharp edges and take all the curvatures and make them very gradual and very blended in such a way that any radar energy will strike the skin, move gradually over the skin, and be absorbed at the other side of the airplane. So taking these concepts of the smooth blending and the fact that you have two humongous engines and a weapons bay, which has to hold many missiles but can't hold them outside because the missile will have as much radar cross-section as the airplane itself. So you have to put the missiles inside, then the engines have to go somewhere, the inlets have to go on one side or the other, and there's a competition for space. You try all of these different combinations until you find just the right combination or compromise that makes it work.
RCS is a short version of radar cross section.
How does that? What is it? How does it work?
Radar cross section is an equivalent area seen by some kind of radar for this particular objects you are trying to detect, acquire, and just equivalent area. It's defined by square meters. And the electromagnetic waves, as I described at the very beginning, is a radio waves and cover all the frequencies from acoustic to UV. So we are talking about AM, FM. In the radio, VHF, UHF, it's a very tiny portion of the frequency spectrum. Sometimes we call it DC to daylight.
The low-speed tests, we're only going to go up to a maximum of 30 knots ground speed. And we will evaluate how the airplane handles on the ground. We will evaluate the nose wheel steering to give the pilot a feel for how the airplane will handle when he has to taxi out for first flight. Paul is an important part of our evaluation. He's the one that will give us his evaluation of how the airplane handles. And Paul has been doing a lot of preparation for this, the low-speed and high-speed taxi tests at Mac Air's ground-based simulators where we've been doing a lot of our low-speed and ground handling simulation. A lot of the work that Paul has done there will be give him the feeling for the airplane, so that the first time he gets in the airplane, he has an idea how it's going to handle. But he will verify that now during our taxi tests.
Work. In 1990, I could never have dreamed of 25 years later coming back to see some faces that were very near and dear and remain that way to me. There are some consummate engineers in this audience right here who brought this airplane to life. Jim and I had the extreme pleasure of having the best seat in the house, but we never forgot who put us there. So let's see a show of hands. How many of you worked on the F-23 program in some form or fashion? Excellent. Fantastic, and my thanks to all of you and those who aren't here for what you did. And what I want to do and what Jim wants to do is give you some idea of what we did back then and what was so revolutionary, truly revolutionary about what we did and what we were able to pull off. What I'm going to do is have the talk in three pieces. First, I'm going to take us back to the beginnings of the program, and you'll be surprised how early this concept started. I'll tell you the background, I'll tell you why it was important to build this airplane or this class of airplanes, and then we'll go into the test program and the people who helped make that happen. Jim will cover that portion of the program, and then I'll come back up and finish up with the conclusions on it. I will invite your questions. We'd like to hold them till the end, but we look forward to your questions and particularly your insights because much has been lost historically from this program. So some of it is in your heads right here, and we hope to tap into that today and learn more ourselves. It was a quarter of a century ago, and yet as I look at this picture and as I look at the airplane, I'm still struck by how futuristic the airplane looks. It was quite a different shape then. It still is now. The interesting thing is, though, that it was almost a half a century ago that the germ of the idea for this airplane began, 44 years to be more precise. But it was 1971, and the U.S. Air Force began thinking about the next generation of fighters. It's curious to look at the time frame, 1971. The Congress of the United States had granted funding for 3 brand new fighter aircraft for the Navy and the Air Force. 3 fighter aircraft that hadn't even flown yet. And yet here's a bunch of people thinking, well, let's talk about our next toy. And you can only imagine what would happen if the Congress had learned that they were out there trying to come up with something better than the airplanes that they didn't even have in their hands yet. How greedy can you get? So the question is, what was the Air Force thinking? And why were they thinking it? So that's what I want to show you. If you take the 100-year sweep of aviation and combat aviation, 1915 to 2015, you see some interesting parallels. At the beginnings in World War I, the airplane was a weapon, and the weapon of choice was a machine gun, and the machine gun is mounted pointing forward. And for every weapon of war, there's a counter to the weapon of war. And the counter to the weapon of war was a gun on the ground shooting the airplane in the air, which was shooting its machine gun. And initially, it was just nothing more than a piece of artillery that was mounted on a swivel, and you try to hit the airplane with the rifle caliber or cannon caliber guns on the ground. But there was a break or an introduction of something new right after the Korean War, and that is instead of bullets, they began to put missiles on airplanes. Missiles are much faster, they're more maneuverable, and they have longer range than a bullet. And of course, for every weapon, there's a counter to the weapon, and it turned out to be a missile that would go up and get the airplane and take it down. But the real key to the difference here is that the first picture with the World War I fighter, you're looking at what's called ballistics. You shoot the gun, the bullet leaves, and once the bullet leaves the muzzle of the gun, it's gravity and aerodynamics that determine where that bullet goes. And if the target moves ever so slightly from the time you fire the bullet, it misses. The bullet will miss. The difference here with these weapons after the Korean War was that you fire the missile and a radar looks at the airplane no matter what it does and guides the missile. The missile can redirect itself in flight to chase down the airplane. So you can refer to this advance in air combat as creating bullets with a brain. And let me give you an example. This is a missile system from the Vietnam War. It's called a SA-2. Soviet doctrine was to fire 2 missiles for every airplane that they wanted to hit. They fire them 6 seconds apart. The missile has a big booster, shoves it up, and then the sustainer rocket takes over. You can see the contrail beginning here as the missile climbs up and away. This actually happens to be a test shot, and you'll see up top a parachute with an object on it. It'll show up here in just a minute. There it is, right here. And this is the target right here. So the radar is directing that missile, and look how it can move so rapidly, change direction, and blam, it hits it. Now the pieces are starting to fall down, but there's a piece that falls down right about here. There it is. This missile is being directed by the radar. It's going to take care of all the pieces. So you can kind of imagine what that's like from a pilot's point of view in the airplane. That really is a bullet with a brain in it, and there's very little you can do to outsmart it. This is a picture taken 3 seconds later. 3 seconds before this airplane, this F-105 here, was right here. And at this point, a surface-to-air missile came in from the left side and exploded. And when they explode, it's like a shotgun. There are thousands of steel pellets that come out, and it hit that F-105, and then 3 seconds later, you see it on fire and going down. This became a major loss creator for our aircraft in Vietnam, and we had to do something about it. This is what the system looked like. It was the missile on the ground that you just saw. It was a special radar that could track very precisely the airplane in flight, which you also saw it tracking. And that radar could control the missile. So the solution back then was, okay, cut the link between the missile and the radar. And the way we did that was 3 things. We used chaff or window that was used in World War II initially, but we used that in Vietnam. That creates noise on the radar scope of the radar operator, and he can't see the airplane for all the noise. We used jammers, special pods that could actually interfere with and destroy the signal of that radar on the ground, again, cutting the link. And then third, we would just get low altitude to where the radar simply can't see you because there's mountains and dirt in between you. All of those things have negatives about them. For example, train masking, you're so low and going so fast that it's hard to see any target, and you're gobbling up fuel at a great rate. But that's all we had at hand in 1972. And it was getting a lot worse. In the upper left side, you see the Soviet airborne warning and control airplane. When introduced, this allowed this airplane to get up at high altitudes and look out at very long distances and look down against the ground and find our airplanes. Once they found the airplanes, then they could direct the fighters, and you see in the upper right and the lower left, the Fulcrum and Flanker aircraft, the Soviets' newest aircraft at that time, very maneuverable airplanes. But the real key to these airplanes was they had radars that could also look to the dirt. And they had missiles that could go down into the dirt and find us even though we were down at very low altitudes. So suddenly the sanctuaries that we had in 1972 were disappearing. And the Soviets were putting out the next generations of these surface-to-air missiles that were now faster, more lethal, and were more resistant to our jamming and attempts to cut that link between the missile and the radar, and the missile and the radar. So we had to come up with something new because this was keeping us from using our F-15s and F-16s and F-18s in highly defended areas. We just could not get through the defenses. So the government spent 10 years looking at ideas. That's what happened in 1971 to 1981. It was only 10 years later in 81 that they asked us, the contractors, to come in and give us our ideas of how to work this problem, this thorny problem. 9 companies were offered the chance to get involved. 7 companies took the government up on the offer. And they gave out a bunch of designs. You see this here on the left side. They're divided into air-to-air solutions and air-to-ground solutions. They also are all over the map in terms of size and weight and capabilities. The Lockheed airplanes down here in the right corners should remind you of an SR-71. They're based on that huge airplane, huge, 115 feet. This airplane I think is about 63 feet, and theirs was 115 feet long. So they were monstrous things. Northrop's up there in the upper left-hand side, small airplanes, kind of our heritage. But interestingly enough, nobody at this point in time had thought about stealth. These tended to be non-stealthy airplanes. On the right side of the picture, the three airplanes you see are parts of the evolution of Northrop's airplane, which eventually became the YF-23. And you can see there's a lot of things that were explored. The one in the middle is aptly called the Christmas tree. Well, how much did we know about stealth? Actually, we knew almost as much as Wonder Woman did. She recognized that it was invisible, that if it was invisible, it was going to be difficult to see. Okay, that makes sense. But she also realized, quite intuitive, that somebody would pay a pretty penny for the ability to have an invisible airplane. And they were right, because it was going to be expensive. We were treading new areas here. Stealth itself is a concept. What is that? That is the ability to create an airplane that's invisible, in simple terms. Not truly invisible, but so tiny that it's hard to see, hard to pick up with these radar systems we're talking about. These concepts were explored in World War II. The Germans built this airplane, the Horten 229, twin-jet fighter. It turned out that it was a subsonic airplane, but very maneuverable. They did fly the first vehicle in December of '44. They had the first production airplane finished, ready to go out to do the test flights when the American forces took over the airfield in April of '45. So it came close to being operational. It turns out it was very stealthy for the radars of its time. Even the skins of this airplane were made out of crushed carbon and plywood to absorb radar energy. So they were well into the concept of making airplanes invisible. We call that Generation 0. Generation 1 is represented by the SR-71. You see an airplane that is very fast. This is Mach 3 kind of range we're talking about. Pretty much goes straight and level. It's not a maneuvering platform, and it carries a limited amount of payload internally, cameras in this case, but it can go long distances. Turns out that this airplane was shot at many, many times by those surface-to-air missiles we saw earlier, and never once did they come close to taking it down. And it's not that stealthy. What it does have going for it is speed. And speed, if you're a skeet shooter, you know the faster the skeet goes, the harder it is to hit. And so you're going Mach 3, these missiles can't catch you. And it was part of its survivability. One reason why we also wanted to adapt that characteristic for a fighter. The second generation starts to look not like airplanes, but frying pans flying in formation. These are called faceted designs. Notice every piece of this is a flat plate of some kind welded together in a shape that somewhat resembles an airplane. High subsonic again, not fighter maneuverability. It didn't have the capability of being a fighter, but medium maneuverability. It carried the payload internal again, because if you carry a payload external, it destroys your radar signature. And it had limited range. The airplane could be air refueled, but by itself it didn't have that great a range. Generation 3, Northrop gets into the picture, the B-2 bomber, and this is near the end of the 70s. High subsonic again, pretty much straight and level again, huge payload by comparison with the other airplanes, and long ranges. So if you're keeping a scorecard, the scorecard looks like this. We determined that the next fighter that we built had to be stealthy, invisible if you will. It had to be able to go long range on supersonic speeds to help defeat those SAM missiles. And it had to be highly maneuverability because it was going to be an air-to-air fighter against other fighter aircraft. And you'll notice that if you read across there on each one of the generations, we never got there. What you and I and the rest of the folks who were on this program were asked to do is create something that never existed. An airplane, a true fighter, that had all of those characteristics together. That was revolutionary and is going to be a watershed mark in the design of airplanes. It's the introduction of stealth technology to fighters. So the challenge was we had to be invisible and omniscient. And let me just give you an analogy what that means. You know about the patrol cop that wants to go out and catch a speed. He takes the car, he parks it behind a bridge abutment, behind a bush somewhere, so that he becomes invisible. Okay? Next, he takes out a radar gun and he points it at you and it's going to catch your speed and then give you a ticket. Right? But his failure occurs in the omniscient phase, the all-knowing phase. That radar gun puts out energy and you buy a fuzzbuster and you see him looking at you, and he gives himself away. So it was important for this class of airplanes to not only be invisible, but they had to reach out and touch someone, and you never knew they were there. So that was our challenge. It had to be highly maneuverable. I've already mentioned that. Long-range supersonic and the large internal payload for the missiles. So those are the requirements that we worked to. The program that we were on was called Demonstration and Validation, or DEMVAL. And what was unique about it was that we were not constrained to the 1986 technology. In fact, the 1986 technologies would not have gotten us to what I just showed you. We could not have been omniscient, for example, in 1986. So we were asked to stretch the technology and think about it and demonstrate pieces of it that would represent what was probable in the year 2005. We defined, the contractors defined, Lockheed team and the Northrop team, we defined what the ATF was. We didn't have specifications, big long specifications. We were able to run the test program to test what our portion of the our airplane technologies did. The programs were not the same between the F-22 and the YF-23. And interestingly, we were asked to cough up money, and we, Northrop and our suppliers, coughed up 1/2 the cost of this program. And the U.S. Air Force did a great job of leading it. They had the concept of letting us, the contractors, try it out and experiment. And the result was, and quite unusual historically, both the YF-22 and the YF-23 were successful designs and filled the mission requirements. So here's some little known facts that many of you may not know. There initially was not going to be that airplane. Just up until about 3 months before the proposal was to be put in, we got a change from the government that said build prototypes. So we scrambled to do that. And interestingly enough, there were really no requirements. You had to fly one time. I'm not even sure they specified you had to land successfully. But there were no specific requirements. It was not a fly-off, as many people suspect it was. It was not, because the programs were totally handled independently. The testing was done independently, so you can't make an apples-to-apples comparison between the YF-22 and the YF-23. They were quite unique. And we were way beyond the state of the art, and particularly the avionics. I think that the avionics is probably the key to this airplane, not so much the airframe you see out there, but we were working way out on the edge of computer technology in that time, in the time frame. And $1.1 billion is what we coughed up. A lot of money that did not, unfortunately, see fruition. I want to transition now a little bit into the test program and give you an idea of what we did. The program was highly classified, up to top secret and beyond. And unfortunately, even the flight reports were classified. So today, I don't have access to even what we did as far as the details go. And much of the classified has been destroyed. So pardon us if we make mistakes, let us know, but some of this comes from our memories, and precious little information remains. One of the things that happened right away was people said, you can't show the airplane to anybody. This is before we had to roll out. We had the airplane at Edwards. They said, you can't let anybody see that airplane. But we had to take the airplane out and go down and run the engines and do fuel checks and other things away from our hangar, so we had to move the airplane. And we said, well, how are we going to do that? And we got these spy satellites flying over the top of Edwards Air Force Base. You don't want us to show the airplane. How do we do that? Some brilliant engineer back at the SPO said, well, look, when we have you transport classified information, it has to be double wrapped. You wrap it once and you wrap it twice, and that way you hide the classified information and nobody can see it. So you double wrap the airplane. Okay, so this was the solution. Now, nobody thought about the fact that the wind blows a minimum of 30 miles an hour at Edwards Air Force Base. But there was a saying back then, don't get mad, get glad. The Glad company was just delighted to see us here. Obviously, this didn't last too long before people saw the lunacy of double wrapping an airplane. Okay, this is PAV 1. This is PAV 2 out here. But you'll find today, if you crawl underneath the airplane, you'll actually see the scoop underneath the airplane. And the guys were kind enough this morning to wrap foam and tape around the edges of it, because there's a very sharp scoop on the bottom of the airplane. And it's open on the ground until you get up to flying speed, and then it closes back up. And we had one of our crew chiefs crawl out of the airplane one day and take the point of it right in the forehead, and it was a nasty little cut. So we decided, well, we have to be safe. So we'll paint a little red triangle onto that scoop, which you'll see out there. And then I said, well, why don't we put another triangle just to accentuate that this is what you're interested in, is this area here. I don't know, it kind of looked like a black widow spider. So anyway, that only lasted a short while before management thought that that was inappropriate, but it did appear on the cover of Aviation Week right after we did it. Bob Sandusky's not here, but Bob Sandusky ran a small team of people embedded in the B-2 program early on, like before the Air Force came to us and asked us for our opinions. And they were looking at the very same problem. How do you make a fighter out of this technology? And they took the B-2 technologies and the concepts and began experimenting with it, and it resulted in the YF-23 as you see here. And this picture is kind of a testament to the fact of who was my father, and the B-2 was the technology was the father of the YF-23. Well, we're looking at the operation of the nose wheel steering and the brakes predominantly today. And as you might imagine, they're a bit more complex than your car steering and brakes. So we have a number of different modes that we operate in. And we tested all those modes today, and it was extremely successful. The airplane is a solid performer and taxis very well. Brakes are excellent. We had a blistering 30 knots, which is about 35 miles an hour. But that's a normal build-up approach that we use in flight tests. We start there and, of course, build up to higher speeds, which we'll be doing very soon. I've been looking forward to this for 4 years, and a first flight for all my life. So for me, it's just the threshold of some very exciting times that we're going to have together as a company.
Version is being built by a team made up of Lockheed, Boeing, and General Dynamics. It will be unveiled later this week. Now, whoever comes out the winner in this high-stakes dogfight will be awarded a multi-billion-dollar contract to build 750 of these new advanced tactical fighters. No dogfights here.
Week in a competition for an Air Force contract. If Northrop gets the bid, it'll mean thousands of
America's newest fighter plane. A team of engineers from Northrop and McDonnell Douglas unveiled their fighter of the future today at Edwards Air Force Base. It's the ATF, Advanced Tactical Fighter, and it's designed to replace the Air Force's F-15 fighter jet. Here's what the pilot who took the ATF for a spin today had to say.
The airplane appears to be very clean, much cleaner than we expected. During the climb out, I was using considerably less power than I expected, and the chase airplanes were an afterburner just to stay with me with my landing gear down.
The fighter jet will cruise at 1,000 miles an hour. Northrop and McDonnell Douglas hope to win the Air Force contract for the fighter. Lockheed, Boeing, and General Dynamics have teamed up to design their own model. It gets its first test flight on Wednesday. The winner gets the multi-billion-dollar contract. That's how that works.
It was not the fastest airplane of its time, but it was the fastest tactical airplane in terms of being able to sustain very high speeds, long enough to actually perform a mission. Typically, prior to that time, fighter planes would only fly supersonic for brief periods to either catch up with an enemy that they were trying to shoot down or to run away from one that was trying to shoot them down.
I worked on the F-4, I worked on the F-15, and obviously I worked on the F-23. The maximum speed of all of those airplanes is not that different. What is different is how much thrust they use to get to that maximum speed and how long they can cruise at that speed. That's really what the benefit of the F-23 was.
The dry engine thrust was massive. I don't remember the exact number right now. It was over 30,000 pounds of thrust out of each engine.
In terms of thrust, I think these are something like 50,000 pounds thrust engines, if I remember correctly, which typically the way engines have been developed, at least in the time I've been in the business, is most military fighter engines have what they call military power, dry power, where the afterburner isn't burning, and then they have a significant increase when the afterburner lights. What we found was when we went from the J79 to the F100, and then we went from the F100 to the F119, the full power afterburner of the previous engine was matched by the dry power or military power setting of the new engine. So really a tremendous improvement in performance in each one of these engines.
How did it compare to the Lockheed F-22?
We cannot make comment on that, but with all the indications, we are at least as good as theirs in every aspect.
But it was a heck of a flying machine. We know it.
Where's Bill Flanagan? We never would have got this picture if it hadn't been for Bill Flanagan, but by God, he fought it every bit of the way. Bill Lowe was in that fighter jet. He was out doing a flight test. I was a safety pilot in the mission control, and realized that, had just heard by a rumor that our friends in B-2 land were flying. At that time, they were still very quiet about what they were doing. I happened to know Bill and somehow got in touch with him, and I said, "Hey, when are you going to land?" He says, "I can't tell you." And he wouldn't. So we played a guessing game with little secret numbers, and we were calling back and forth, said, "Well, will it be 10 minutes or 45? I can't tell you, but it's not 10. So when Bill Lowe came back and finished his mission and taxied on back, we said, "Wow, it looks like there's an opportunity that we might not ever see again. Hi, Ed. Good to see you." And so we had Bill Lowe taxi on out to the Hammerhead by the approach end of the runway and sit out there and wait. He said, "How long do I have to wait?" I said, "I don't know, but we'll find out." Sent the photographers out there and got a world-class picture, and it's my very favorite picture of all. I just happened to have the opportunity to have flown both of those beautiful airplanes. So we'll talk back to the YF-23. A lot of unique shape characteristics to it. Some of them are because of the stealth characteristics that Paul talked about. Some of them are because of the aerodynamic characteristics that were required from the requirement to be able to fly very fast, fly very high, fly for a very long period of time, not use afterburners, not use too much fuel. Another thing that is interesting, as you can see on the airplane out there and also in this picture, these tremendously large vertical tails. Well, they're not vertical tails, but the things that are hanging out there, the world's fastest bonanza. In addition to the aerodynamic characteristics that it gives to the airplane itself, the rearward field of view is just absolutely panoramic to the fighter pilot. And that's just exactly what Paul's talking about with the picture window form. Also, the air data system on the airplane was designed to have flush ports. That was unique for a fighter airplane, certainly unique for something that was going supersonic. Our friends in B-2 land had been using flush air data systems before. You might see as you walk around PAV-2 here that we also did have L-head total temperature and dynamic pressure ports, and that was primarily as a backup. We were using that for flight test data in order to validate what the flight controls were using. The sinuous ducts, if you look at this as well, the face of the duct is actually one diameter below and to the side from where the engines are themselves. And that's very important from a stealth standpoint, that there's no radar that's going, beams that are going to get into the duct and into the face of the engine that's rotating, which is a very highly reflective radar reflector, and get back on out. And the exhaust duct, we'll look at it a little bit later. Beautiful planform. You get to see the airplane on the side all the time. Not too many people other than pilots get to see the planform, what it looks like on the top. Big part of the design was the edge form alignment planform. So as you look at the airplane that's leaned up there on the side, you can look at and see the large number of lines that are all aligned together. So that radar, whatever radar reflection that the airplane did do, was restricted into known areas. Part of that reflection gave a distinctive figure
on the radar scopes that was reminiscent of a eight-legged insect, such as perhaps a spider. And when you look at the top, you can see the planform. Also here you can see the exhaust system, and you can see it when you look at the airplane out here on the side. The exit of the exhaust, including the afterburner, was well forward of the back end of the structure. So the trough that was back there was specially constructed out of careful materials with some active cooling. It was designed by Allison, I think, to do a tremendous job to allow us to use afterburner without burning off our own tail. So that was unique. And that was one of the things that was a little bit different between the two airplanes, because the Pratt & Whitney and the General Electric engines had different upper flaps in the back. Also, another characteristic is that look at the size of the vertical tails, if you will, the tails themselves. These are tremendously large. They're larger than a F-5 wing, almost as big as an F-18 wing. And these devices rotate plus or minus 40 degrees. Well, you'll see when you play some of these videos, it really moves around a lot. And they are driven by extremely high-fast actuators that operate at very high cycle rates, and driven by computers, digital computers, that are really moving very fast. The end result of that is that in order to provide the airplane stability and control, keep it stable, or respond to the maneuvers that the pilot wants, these tails do not have to move very much because they're very large and they move very fast. This is a picture here when we're taking that tail and laid it down, if you will, to show the relative size. It's almost as big as the wing itself. So that's one of the things that made the airplane tremendously maneuverable, and also contributed to its stealthiness, because as the airplane maneuvered, it wasn't waving its wings around a lot. This is a picture of the airplanes that were involved with the flight test program, both from a chase standpoint and the test aircraft, just showing some of the relative size and the evolution from the F-16 to the F-15 to the YF-23 in their shape and the efficiency of their wings. We used a lot of off-the-shelf components in the airplane because they were prototypes. We had to make a lot of inventions. We had to make new things that had never been done before, like the exhaust system on the aft deck, like the intakes, like the bleed air system that was protecting the supersonic shock in the inlets, the flight control system. But we didn't need to invent wheels or pumps or brakes. And so we adapted a lot of stuff that you can see here that came from other programs and other things. Anytime you do that, there's always sometimes a little bit of compromise has to be made. We found during the flight test program that we had to be very careful about the braking of the airplane, because we had F-18 wheels and brakes, which were not sized for a 50,000-pound airplane, even though we weren't landing at 50,000 pounds. So it was a heavier airplane it was designed for, and we had to take care of that, not only from a pilot technique standpoint, but also after most landings, we would plan on parking at the end of the runway, have the crews come out, measure the temperature of the brakes, and be ready to apply cooling air if necessary. Because we had to taxi a long way from the runway back to where we were parked at Edwards. So the flight test sorties program that went on was based on a plan of 2.5 sorties per week for each of the airplanes. And each of the airplanes had a learning curve at the beginning, but they finally did get up on the step, and they met those projections. But we didn't come out before and talk too much about the program that it was established and started in 1986. And so out of those Northrop people that are here, how many people can remember that terrible and wonderful bittersweet day in October of 1986? That was the day when we were told that the F-20 program was not selected by the Air Force, and it was the death knell of the Tiger Shark. It was the same day that we were selected for the ATF program contract. What a bittersweet day. But when that program was selected in 1986, it was to run for 4.5 years with a contract award in 1991, and it was a fixed amount of time. Our original plans for test these airplanes was a 350 sortie plan. As time went along and gang after glee and plans didn't work out and schedules slipped, it got later and later and later to the point where we were only able to fly these airplanes for 3 months and 50 sorties. So that made a lot of difference in the flight test planning and what it was that we were going to do. But the biggest part of the story that we want to make sure, besides the airplane, was all the wonderful people that helped us have the dream of flying these airplanes, and you all had the opportunity to work on something that was really very special. I want to say right now that during the period of time I was on the YF-23, I worked with people that I knew from other industries in our teams. Worked with people from other divisions. And then later, Paul and I both worked with those same people in different programs on other programs. YF-23 people that I worked with on the F-20, I saw on the B-2, or I saw later on the Super Hornet at Pax River. And people that I worked with McDonnell Douglas on the YF-23, I was working with on Super Hornet and Pax River. So this teaming that goes together, not only individual teaming, but organizational teaming was important. Paul mentioned the magic that happened in the computer world in order to be able to provide the sensors and the computers that would make that fifth generational leap in capability. A lot of that work was done on the YF-23 avionics prototype program by companies like Westinghouse and TRW. I think Litton was in there a little bit as well. So you can see it's not only individuals working together later on teams, it's organizations as well. This is a picture of the flight test team gathered at Edwards Air Force Base during the rollout of the airplane. These are just the folks that were working in the flight test at Edwards. There's a tremendous amount of other people, as you all know, that supported this activity, both here at Hawthorne, El Segundo, the electronics division, and all around the country with our other suppliers.
Those numbers are still classified.
I don't believe I'm at liberty to tell you.
It was a very fast airplane.
What numbers are still classified?
That's performance numbers.
Well, I would say at least 2 times the speed of sound, maybe a little bit more.
The only thing I can say is we have documented numbers to show the Supercruise number is very, very good.
They said they supercruised. I don't know the true speed, but it had to be fast the way the YF-23 was shaped. It was so sleek. It had to go fast.
Fastest isn't the measure. Best is the measure, and best is to do what it's supposed to do, win an air battle. And that doesn't always go to the airplane that, like a rocket plane could go fast, but it'd be going somewhere, but it wouldn't be in an air battle.
I have to just interject. It isn't very useful. Now, if you're going to supercruise, that's to get from one place to another, and you can do it for a fair amount of time. That's great. Most airplanes that operate above Mach 2 can't go anywhere. You know, I mean, by the time they get up to speed, they're out of fuel. So it's not as useful as used to be thought.
And more than being fast, it could fly fast for a very long time. Up until the time of this aircraft project, airplanes that went supersonic really could not maintain supersonic speeds for really long periods of time. And the reason was that tactical aircraft, to go supersonic, had to use afterburners. And the afterburners are nothing more than a device which pumps a huge amount of fuel, as its name implies, behind the engine, and so into the thrust flame of the engine, which then explodes that fuel all at once and pushes the airplane along faster. This aircraft had to be capable of what they called supercruise, and using some very specially designed engines, it was actually able to go supersonic without using afterburners, and therefore using far less fuel than previous fighter planes had done.
I know that the supercruise value for the GE engine is still classified. But both airplanes were capable of operating at right around Mach 2.
Well, I would say at least 2 times the speed of sound, maybe a little bit more. Not really sure because nobody's really said anything.
There were 5 pilots that flew the airplane. Paul and I from Northrop Grumman. Bill Lowe was the McDonnell Douglas pilot. We had 2 Air Force pilots, Major Ron Johnston and Major Con Thusen. Although this is a silly kind of fisheye view, that's what we thought of the airplane, every one of us. Even the Air Force guys. Paul put together a plan to train the first flight team together. They spent more than a year in preparation for the first flight, because the first flight was going to be in January of 1990, and it just slipped until August, the 27th of August. But the number of people that were on the flight test team involved a core of flight test experienced people, and then the large bulk of it was people that came from the design activities that actually designed these systems and made it work. So we took the true subject matter experts in each field and worked together to build a team that were able to sit and work in the control room to maintain the test objectives, get the data that we needed, and then also be able to respond to things that might go wrong. It was a tremendous test program. My hat's off to Paul and everybody else that had anything to do with it, because it was a great team effort, so we were able to get that first flight team ready to go. And when that first flight took off, everything went tickety-poo. PAV-1 was a great airplane. It had a minor malfunction with the landing gear indication on the first flight that I think might have cut down the time a little bit. But for the most part, the airplane went very well in its flight. PAV-2, the second airplane, was a little bit later in trail. It flew almost 2 months later on the 26th of October. We also had a flight test team that I helped lead, and we went through similar training. But we borrowed a lot of the expertise of that first flight team from Paul's team and benefited from it greatly. Now, here's a list of some of the names. It goes up. You don't have to know them all, but recognize that it's a combined team. There are Northrop people, there are Mac Air people, there are subcontractor people, in this case Pratt & Whitney for the PAV-1, and we've got Air Force people, not only in the pilot positions, but also in some of the engineering capacities. The main flight test engineer for both of these PAV airplanes were both McDonnell Douglas teammates. So we had Jim Martin for PAV-1, and I had Wolcott Blair for PAV-2, and their able assistants right behind them, the guys who were doing all the heavy lifting, was Les Dowd and Mike Hans. So we went on, and it was a combined team of contractors and players, to the point where Paul wants to make sure that everybody understands that the Pratt & Whitney team was critically important to the success of their flight test program on PAV-1. And I got the same thing, but I didn't get a medallion from the General Electric people. So talk a little bit about the statistics that up there. I mentioned that it was planned for 350 flights. We only flew 50. We only flew about 65 hours. I'll get the numbers wrong because I can't see it from here. But shows the total number of flights that we flew, maximum Mach. We went out to 1.8. That was in PAV-1 because it was the flutter airplane that would go out and clear the envelope. I think PAV-2 only went to 1.7 during one of its tests. Maximum altitude, we're pretty much 50,000 feet. It was just a rule, and the total number of flights for both of those airplanes. The big difference between the two airplanes, about the only difference other than the instrumentation, was the engines, because this was a competition, although not a fly-off competition, between two airplane designs and also between two engine designs. These were the envelope that we explored as far as we went, when the first flights were. Longest flights, 3.3 hours. Obviously, we had air refueling for those, and we relied a lot on air refueling, and the speeds that we went on through angle of attack and side slip. So it was a compressed, very compressed flight test program where we had to tunnel through the envelope in order to get to the points where we wanted to do. We wanted to prove Supercruise, so we wanted to get out there to those Supercruise positions. We wanted to demonstrate level 1 flying qualities throughout the envelope, and we had to do the air refueling, etc. But not everything goes great on every flight test program, despite the fact that PAV-1 was a great team of professionals, and they were going off and probably went through flight 6 before it had anything that untoward. PAV-2 was a little snake bit, and it wasn't because of the team, it was just the way things were. So I'll talk about the first flight that we had. When I did the first flight on this airplane, and my team as well, I thought we were kind of in the rocking chair. Boy, the Lockheed Martin guys had flown the General Electric engine long before on their first flight. Paul had already flown the PAV airplane, the YF-23. We knew that it worked. Everything's pretty good. Well, this is a true first flight because it's the first time together with a new airplane and a new engine together, but we thought everything should be okay. The Air Force required us to go through a long process for a first flight of briefing ahead of time, going out and practicing with surrogate airplanes to practice a first flight, to help the crews practice and help the instrumentation people practice, help the people in the tower practice. I argued a little bit to say, do we really need to do this, particularly taking off on runway 04, which is opposite the normal direct flow of traffic, but said we have to do it because we have to be safe. We were. Paul's the chase airplane in the F-15, just told me to release the brakes. I released the brakes, the airplane's rolling down the runway. I look down the runway, I see a light at the end of the runway. I think there's a truck on the runway. I said, oh, I think there's a truck on the runway, and then the light went out and turned off to the side. I said, well, he's off of the runway now, so we'll keep going. On the other side of the airplane is the F-16. He's the photo chase. I mean, no, the F-16 is the safety chase.
That's good. Now, it's running and climbing with you. Whoa, keep your knees up. Jesus. Jim, you're clean and dry, looking good. Did that call you ready pretty good?
Yeah, there was an airplane landing on the runway in the opposite direction, but despite all of the practice, all of the briefing, all of the special procedures which were taken care of to avoid that possibility. And, oh, by the way, the fact that it happened to be our own Roy Martin in a T-38. Lieutenant Colonel Roy Martin on his reserve duty at the test pilot school on an instructional sortie. Well, communications broke down in the tower cabin, but boy, I'll tell you, that could have been a real eye-opener. Thanks, Roy. Actually, the thanks is Roy's student who was in the front seat, and he's coming down, and he says, I think there's an airplane on the runway. And Roy says, where? And he looks and says, wow! So when I was a young test pilot, came to work for Northrop, Darrell Cornell would brief me on how to fly airplanes with their, came right out of the hangar, and he said, when you first take off an airplane for the first time, put the landing gear up and then put the landing gear down. And when I put the landing gear down, we had that crazy condition there with only the nose gear down. We thought about it for a long time.
Just west of the field. And you're clear.
The only thing we could do was to raise the gear up because we couldn't land with only the nose gear down. Recommend that we leave them down. Our trusty test chase pilot. Thank you, Taco. I agree. That was on the second flight of PAV-2 was when we went up and we did the air refueling test. And the first time we went to the air refueling, and that's when we recognized a significant, about the only real significant pilot difference between the two airplanes. The General Electric airplanes were very, very powerful, but they were also very, very responsive, but they weren't well coordinated with the throttles, and it was very difficult to do very close maneuvering. And the first time I went to the tanker, because I'd already been to the tanker in Paul's airplane, and I got there and I said, I said, I don't think I'm going to be able to do this. And then finally, I got an inspiration, and I put one throttle at idle and the other one up in high power, and it gave me enough good, fine linear control to be able to do it. So we left the tanker and said, now we're going to go off and do some real testing. And about that time, I had an engine malfunction that came up, and we had to return to base on the second flight. Declared an emergency. So then on the third flight, Paul's chasing me, and we're going off, said, all right, now we're going to go off and do some real testing. Everything's all set. Took off, we climbed on up. We're climbing through about 27,000 feet. I think before that, 19,000 feet might have been the highest we went. And as we passed through 27,000 feet, Paul gives a call and says, you're venting. And about the same time, the control room saying, descend. Don't know what's going on. We'll pull the power back and we descend. And there was a problem with the pressurization equalization in the fuel tank, which had allowed the fuel tank to overpressurize almost to 150% of its design load. And if number one, the vent hadn't been there, but most important, we had sharp people in an instrumentation room that were watching data, and they saw something that they did not understand, didn't know why it was, and they weren't expecting it, but they knew that we had to do something and called us to descend, probably saved the airplane, might have even saved my life. And I thank whoever that was. Thank you very much, Fuels. Fourth flight, Paul said, that's enough. I want to fly this airplane. It's about time to get out of here. You're just causing trouble. He took it flying, and I went to chase him. So I'll go along and chase him as well. And we were out, and we were flying Mach 2, Mach 1.5. Paul was flying it, doing the envelope, going out to the envelope that he had already cleared in PAV-1. And the windscreen cracked. Here you can see a picture, I think, of the windscreen cracked. It had happened previously on PAV-1 at a lower speed, probably around flight 9, something like that. So there was a problem with the design of the windscreen. In fact, there had actually been a windscreen that had cracked in the hangar long before the airplane was put together. So that was a problem that we had to resolve, but we didn't have time to solve it technically. We were able to solve it brute force. Thankfully, there was somebody that supplied sufficient parts so that we were able to replace this and then continue the flight test program. But I guess if we'd had a longer flight test program, we probably would have run out of windscreens. Supercruise was one of the main things for the program, something that we had to demonstrate, and this is a demonstration here of the way that the airplanes were configured, if you will. The number one YF-22 was powered with the General Electric engine, and the number two Lockheed Martin F-22 was with the Pratt & Whitney engine. That configuration was reversed for us, don't know why, but PAV-1 was equipped with the Pratt & Whitney engine, and PAV-2 was equipped with the General Electric engine. The difference between the speeds for both of those airplanes was dependent only to the engines themselves, and it's interesting to see that when the Air Force made their decision, they selected the airplane on the left, which was the Pratt & Whitney F-22.
Let me make some closing remarks, and I will warn you ahead of time, this is not Northrop speaking, this is Paul Metz speaking, this is my own observations, and you can take them for what they're worth. I have come to learn that in prototyping competitions, like the YF-23, YF-22, there is a tangible and an intangible perception that you leave with your customers. Northrop is, in my opinion, the finest aircraft engineering company in the world. They very accurately predicted the YF-23 and other airplanes that I was fortunate to test with them. And so the engineering skills are beyond compare. So Northrop sees things in those terms, in other words, engineering terms. Let me show you a graph. Let me show you what the airplane does. They match, therefore you can trust me because I can predict what my product will do. And that's very important, and Northrop is unparalleled in that ability. But there's another aspect to this competition. Not everyone that will look at your airplane or even be in a position to select your airplane will necessarily be an engineer, and they may not be astute technically. So there's another way to leave an impression. Some people say this is the picture that sold the F-16. The F-16 is the airplane flying the inner circle, and the F-4 is the airplane flying the outer circle. So your gut reaction should be, give me that F-16, that thing can turn. But we don't know today what were the conditions of that picture. We don't know if the F-4 was simply flying a constant speed and the F-16 was hauling back and making as tight a turn as he could, but also losing his airspeed in the process. We don't know any of that. But it leaves a lasting impression that you'll remember after you leave this briefing here. So pictures are worth 1,000 words applies in a technical, competitive competition, just like it applies in real life for any other things we do. And Lockheed understood that. And they left impressions. They took their airplane and flew it to 60 degrees angle of attack. You see that here in the left and the upper right. High angles, what's called high angle of attack. It's a very exhilarating thing. It's a meaningful thing to fighter pilots. And they have photographs of 60 degrees angle of attack. Now, it turns out that that airplane right there will do that exact same maneuver and stabilize at that exact same angle of attack. In the lower right side, you see a missile coming off the airplane, fire coming out of the missile, and this is a warplane. We're leaving an impression. The reality is that's a very benign shot. It's not a stressing shot for the missile. The missile comes out and flies away quite cleanly. Very benign. In fact, the high angle attack testing portion was relatively benign. There wasn't anything severe about it. Yet you and I and other people are left with this lasting impression of what that airplane is compared to that airplane. And it becomes part of a decision-making process. So I look back on that and said, I hope we learn our lesson that sometimes there's showmanship as well as technical excellence, that you have to play that game. I'll wind up here with one comment. Some of you that know what my career was following this and a short stint in the B-2 program. I was hired by Lockheed to make the first flight on the F-22 Raptor. No pilot ever flew both of these airplanes, both of the prototypes. by design, by intent. They never allowed that to happen. So you'll have to keep that in perspective for what I'm about to say next. I've had a number of people come to me over the years, and we've talked about the YF-23 with great fondness, and lamented the fact that we were not picked. And I tell them, like I'll tell you, that never hang your head in shame about what we did. We built a tremendous product that would stand side by side with anything else, and in many cases exceed the capabilities of anything else. And we can always be proud of that. So I thank you very much for your attention, and Jim and I will be happy to answer questions. Question is, how fast can these things go? And the answer is it's designed for Mach 2. The airplanes went out less than that. They had far more capability, we could tell that, but we never tested them to their maximum speed.
The question is, how much did the thrust vectoring equation enter into the decision-making equation? In that the F-22 had thrust vectoring, the F-23 did not have thrust vectoring. And that was a conscious design decision by our design team. We talked about the tandem wing. We talked about the tremendous size of that tail. We talked about the 40 degrees of throw that it has, driven by high-speed actuators. Thrust vectoring provides some increment of additional pitch control, and pitch control only. That increment of pitch control, compared with the tremendous amount of control power that we had, was not determined to be critical. The results that we got from that we heard from the evaluation of the airplanes leading up to contract award was that the evaluations were based on stoplight usage. There was green, yellow, or red, and that both of these airplanes were fully capable and green, so that the design or the award decision was made by the Secretary of the Air Force Rice, and it was made, quite frankly, it must have been made on non-technical issues because the technical results were equal. Both airplanes were qualified.
Yeah, and that was actually the official wording of Secretary Rice, was that both airplanes met the requirements. They had greater confidence that Lockheed could manage the program. So nothing that we did was detrimental as far as we can tell from the selection process. Yeah, the question is, what role does a simulator play in preparing you to fly something like this? I flew the simulator so many hours I could puke.
The airplane flew just like a simulator, and you say, people always say that. Today they do say that, because the airplanes are designed by the same computer technology that generates the flight control laws, that generates the simulators that you use, that generates the airplane performance. You saw from those graphs the tremendous amount of correlation between actual flight test data and what we were expecting. And what we were expecting is what we flew in the simulator. So every pilot that flew the airplane said, well, yeah, it flew like the simulator. The question is, when we did Supercruise testing, did we have to use afterburner to punch through the number? This is an interesting question. I did the Supercruise tests on both engines, both airplanes. We started at 0.85 Mach, 42,000 feet. We went to full military power, and we just continued to watch it go until it cooked out. And it would be amazing to me in my experience that when you got into the transonic area, as I was watching the numbers tick off, it was 0.97, 0.98, 0.99, 1.0, 1.101, 1.02, there was no hesitation. I did not have any sense of the transonic rise at all. So that was very impressive. Now, another way of doing the testing, which would be more efficient, was to go to full afterburner and get very fast and then take it from the fast side, go into military and see how it cooks down. We selected to do that test because we got a wealth of piece of S data from 8.85 Mach all the way on up.
Question is, what followed from this effort into the future? I told somebody a while ago, this is only 1/3 of the program you're looking at. And 1/3 is the avionics of this airplane. My opinion, the avionics are the most important part of this system. Remember I told you about the omniscient, the ability to see things but they can't see you? That is an incredible amount of computer sophistication. And so I think that's what carried forth. Northrop had a complete organization for avionics development. And in fact, I've spoken to several folks here that were in that group. And we reached out, way out in time. And that type of architecture technology, the way the computers operate, yes, that has been carried into the future, more so than just the nuts and bolts of the airframe. Okay, well, he's asking how much fun was it, you know? And there's the old adage, which is it's the most fun you can have with your clothes on. You know, it is fun. It's exhilarating, but we're trained to get rid of the emotion. We have switches in our brain that let us turn it off and concentrate exactly on what's going on and let the rest of the world be pushed away. So as bland as it sounds, we're unemotional in the airplane. We concentrate very deeply. So, but it is an extraordinary and rare occasion for a pilot to make a first flight on an airplane.
That said, when we were preparing for the first flight and Paul was going to be flying the airplane for the first flight, I worked with the people who were making up the test cards and made sure that the flight test conductor, there was a point in the flight after he got on up and everything was just a point in between points where the next test point was look out the window and enjoy.
Thank you very much.
The sound on the airplanes actually can't be tolerated by the human ear. So you really don't hear the airplane because you have to wear double protection, earplugs and then ear muffs over the top of it just to be in the presence of the airplane. It was so loud that as the airplane would take off, you could physically feel the sound in your sternum. Your chest cavity would actually vibrate and resonate just from the sound of the airplanes. You could feel the sound through the soles of your feet bouncing off the ground. Pratt & Whitney built its test facility in the swamps of Florida and did their engine testings out in the Florida swamps so that they'd be away from population. Well, they put in a PGA golf course many years later, and the civilization moved out there, and the people got used to the sound because they tested mostly at night, and the alligators got used to the sound because they tested mostly at night. But the first time they ran the engine in full afterburner on the test stand at Pratt & Whitney, there were reports the next morning of alligators climbing the fences of people's homes and diving into the swimming pools to get away from the noise. That's a dramatic demonstration of the power of the engines.
YF-23 was very powerful. The engines, I believe there were 38,000 pounds of thrust each. The noise from the engines during idling was something that you could feel it vibrate against your chest. A lot more than you could a regular airplane. And when you heard that thing run, you knew it was running. The power was, from what the pilot said, it was just outrageous. As I understand, the F-16 chase plane had a rough time trying to keep up with it, so they had to move to the F-15 chase plane because the airplane was so fast.
To this day, I think they made the wrong decision. If the criterion was the best airplane possible for the mission. That's what I believe. Are you asking how I felt? That's how I felt.
Even a couple of days ago, one of the key customers, he came to me, he complimented me on our design because he knew the numbers. That's, you know. Another thing I want to point out, if you look at the Lockheed's F-22, it's quite different from their prototype because they incorporated quite a few of our design features. That's the most commentary thing you can say or a designer can get. Your competition imitates your design.
Well, the Air Force has a requirement, very legitimate requirement. It says that the canopy, the windscreen, has to withstand a strike by a 4-pound chicken at a given speed. The spec still says at Vmax. but that's not possible. So it's usually modified and tailored, and they'll require a speed of 400 miles an hour, 350 miles an hour. Something that's close to a climb-out speed or a let-down speed, where you're passing through that region of the atmosphere where there are birds. And you can't design for it. I mean, you can design for it, but you don't know whether your design makes any sense. So you test for it, and it's done in all countries. I'm surprised that we don't get bad publicity about it, because the chicken does have to be alive. You do give them chloroform. Put them in a plastic bag, load them in a compressed air cannon, and fire them at your canopy and windscreen.
How many chickens do they go through a day? They just...
I didn't count them.
Didn't count the chickens.
Now, Great Britain does it in a different fashion. This is Great Britain hangs them hangs them over a rail. Okay, puts the canopy on the rail and fires it into the chicken.
A different way.
Different way. Right.
Those Brits. Those different.
It's no laughing matter.
No, it's
we have lost people due to a bird penetrating the canopy of the windscreen.
Tell us about that.
Well, it didn't happen in the case of the YF-23, but one of the early astronauts, the T-38 is used by the astronauts. They have a fleet of T-38s, an airplane that we made. And early in the astronaut program, one of the astronauts was flying somewhere in Texas, and a snow goose penetrated the canopy and killed him instantly. Bum deal.
So it's danger. The danger of birds, flying birds, is always there.
Yeah, it's real. Yeah. So you have to come up with some way, and you can visualize. I mean, a canopy is this, wraparound thing you look through. Has to have perfect optics. It has all these requirements. Has to operate at certain temperatures, very high and very low. And now you have to make sure that a bird doesn't go through it. And you don't want to make it too thick, because one, it weighs a ton. Two, it's more difficult to keep the optics clear. And so you want to make it the minimum required. And what usually determines that is the bird strike.
Well, I've been fortunate enough to fly the F-16 for 13 years, and I flew the F-15C for about a year. Those are great platforms. They do a great job, and they're a lot of fun to fly. But having flown this now for about a year and a half, I'll tell you, I enjoy flying this aircraft out of all three of them much, much better. The performance, it's a large airplane. It's a little bit heavier than an F-15, but it performs like the F-16. I mean, it'll turn on a dime, and it just handles like a dream. In the Raptor, what happens is it takes in all these signals, and it does all the calculation for you and displays it in one display. So you look down at that display and it displays the battle space for you. So you spend more time, instead of worrying about what the battle space looks like, what your next move is, because you know what the battle space looks like. The jet tells you that. So I would say this jet is much more easy to employ weapons than any other aircraft I've ever flown. I started flying out in Cessnas in Gainesville, Florida, in Cessna 172s and 152s. And after I got in the Air Force, I got so busy that I kind of let my license kind of slip a little bit there. But a couple years back, when I was down at Maxwell Air Force Base assigned there, I went ahead and got my license back up to speed. And that way I could take my family up and take my wife and my kids up and let them fly around a little bit in an aircraft. So I still love to go up in the Cessnas. I still have a blast in them. I just love to fly. It is an absolute thrill to fly this jet. This jet handles like a dream. So when you have the opportunity to actually take this thing off and fly it, I feel lucky every time I just get to sit in a seat and go fly. It's just an exciting day for me to go to work. It is very, what we call user-friendly airplane. It's very easy to fly. Now, employing it as a weapon system, that's a little bit different. That takes some training, and it takes a lot of hard practice and work to get good at that. I really want these folks to understand what this airplane's about and let them make their own judgments about what they see in this aircraft and what they hear from the guys that maintain it and from the guys that operate it. If they hear the truth, it'll sell itself, because this jet is that revolutionary and that significant to our forces that I want them to understand this, and this is their aircraft. We're just the lucky souls that get to go out and fly it every day for them, but this aircraft is made to protect them. They pay for it, and I want them to understand what a good weapon system they've bought here.
about as noisy as this airplane is ever going to get. You can always find out more information about the team by going to our website at leapfrog.navy.mil. Following today's jump, the Navy Parachute team will be available to answer any questions you might have about the special warfare community or the Navy in general. Feel free to stop and ask any questions at any time to any of our jumpers. All right, as our last two jumpers make their way into the road at any time without the proper training. High up overhead, you see two of our jumpers that move together in what we call a biplane formation. That's when two jumpers move their canopies next to each other, then a top jumper will hook into the end of the lower jumper's riser. And effective will look like that top jumper is standing on the lower jumper's shoulders. From that basic biplane, the jumpers can do various other formations, such as the two jumpers that have trailing for his weight. All right, those two jumpers I just told you about in the side-by-side formation are now coming down in that downplane at 60 miles per hour, directly at the ground. As soon as safety permits, they will break apart, track away, and make their own safe entry into the area.
Nobody else in the world has beat them the first time or the second time. So we're proud of saying it takes a B-1B Lancer back to the bone.
I have a B-1 that is taking up a tremendous amount of room, so you got to use a lot of caution out there.
Pounds of thrust. Wings back forward, this should be the last pass. Watch for the pitch up.
Aviation, the art of aeronautics, began with the dreamers, inventors, and daredevils who dared to defy gravity. The journey of aviation was nurtured by pioneers like the Wright brothers, whose first flight marked a historic milestone. The role of aircrafts in world wars was groundbreaking, dramatically changing warfare strategies. This initiated a technological evolution in aviation, transforming the simplistic wings of a biplane into the thunderous roar of jet engines. Let's journey through the ages of aviation. Behind every great aircraft, there were great minds. These visionaries, like Sir Frank Whittle, the innovator of the turbojet engine, redefined air travel. Then there's Skunkworks' Kelly Johnson, the genius behind the SR-71 Blackbird. His designs combined speed, stealth and power, crafting machines that dominated the heavens. The contributions of these pioneers have left an indelible mark on the canvas of aviation, shaping the course of history and inspiring generations of engineers and aviators. Each epoch in aviation history gave birth to extraordinary aircrafts, each with their own unique features and roles. The Lockheed SR-71 Blackbird was a marvel of speed and stealth. The F-105 Thunderchief, a supersonic fighter bomber, was vital in the Vietnam War. The P-51 Mustang, a long-range fighter, was critical in World War II. The P-47 Thunderbolt, a heavyweight fighter, was used extensively in the same war. The A-10 Thunderbolt II, the Warthog, is a close air support icon. The Messerschmitt Me-262 marked a leap forward in aviation technology. Each of these game changers were instrumental in their eras, and their legacies still resonate today. Beyond the game changers, there are those that have transcended their practical roles to become icons. The Concorde was not just an aircraft, it was a supersonic symbol of luxury and speed. The B-52 Stratofortress, a strategic bomber, is an icon of power and resilience. These magnificent machines and others like them have become much more than just aircrafts. They are enduring icons that encapsulate the audacious spirit, the relentless innovation, and the boundless ambition that define the world of aviation. For more amazing aerial footage, and to join us in this incredible journey, check out the Dronescapes YouTube channel.
If you enjoyed this video, please remember to like and subscribe. And as always, thank you for watching.